Okay, guys, I think it's time to get started. At the end of class today, if my lab group would stay behind, I'll return the lab reports from my Monday group. Okay? There's no lab this week, right? You do have lab report due next week for the unknown lab. Some of you may have been contacted by your lab instructor to come by lab this week and pick up your report. I think Dr. Deminda from Friday wanted me to tell you to do that. Friday lab, go there at 2:30 and pick up your report, your graded report from the solubility lab. Okay, back here on the physical properties, we briefly mentioned the acid-base extraction, but I kind of skipped it. Now that we've done acid-base, let's go back and look at this. Acid-base extraction is a very common way to separate compounds. Here we have a mixture of benzoic acid and this alcohol. These two can readily be separated by this process. We can dissolve them in some organic solvent. Dichloromethane is a common solvent in the laboratory. They'll both dissolve. Then we can put in sodium hydroxide. Basically, Tim, one of these can be converted to an ion. If we can convert one of them to an ion, it will go into the water layer, and the other one will stay in the organic. How do you convert things to ions? Acid-base chemistry. Is either one of these compounds in the box acidic or basic? Yes. Okay, I see a carboxylic acid. That's acidic. That's called an acid. Alcohol is not. Okay. Judging acid is a little bit more difficult, maybe. Do you see a base in the box?
No.
Do you see an sp3, sp2 nitrogen?
No.
Do you see anion?
No.
There's no base. So it ain't going to do any chemistry with acids. Nothing except maybe in a mechanism. I'll point out when we do that. Making salts, doing extractions, it ain't going to do any of that because there's no base. Now that's an acid. Is this acidic? Well, you got to know. You got to start learning. The pK of an alcohol is what?
16.
About 16, like water. It's not an acid. Okay? We treat this with sodium hydroxide. Sodium hydroxide will deprotonate the acid, but it will not the alcohol. What do? You add in the aqueous sodium hydroxide. Now you have two layers because the aqueous sodium hydroxide does not mix with dichloromethane. You shake it up and let the layers then reseparate. As you shake it up, the chemistry takes place. As you shake it up, the base will react with the acid, and what will you form? You'll form the sodium salt. Okay? Now you all need to know that because hydroxide will remove proton, you got the mechanism, etc., etc. Some of you need to realize that acid-base reactions are more than forming salt and water. So I saw a lot of that on the reports. You got to fundamentally understand what an acid-base reaction is. Okay? Look at the mechanism page I gave you. Forget about this water and salt thing you learned in Gen Chem. Okay, but this is now ionic. It'll prefer the water layer. Ions will prefer water layer. This remains neutral. It'll prefer this layer. The layers separate because they're not soluble in each other. Once the layers separate, you drain one layer into a flask and you drain another layer into another flask. Now you have them separated. To get this compound, you just evaporate the dichloromethane. You're going to have that compound left. To get this compound, well, you could evaporate water. But another way to do that, because water's hard to evaporate, really, although you can, there's an easier way to get this. If you treat this with your favorite strong acid, such as HCl, what is this going to do to that anion? It's going to protonate it. And when you protonate it, what do you get back?
Carboxylic acid.
You get back the neutral form, and it turns out that's no longer soluble in water, so it will do that. What does that mean?
Crash out.
Solid.
Precipitate. And so usually you can just add acid and precipitate it out and then filter it by suction or something. Because the ion is going to be soluble in the water, but if we can get it back to the neutral form, it will usually not be soluble in water, although sometimes it could be. Sometimes neutral organics are soluble in water, but that one actually is not. So that's taking advantage of the acid base. Sodium hydroxide is strong enough to completely deprotonate this. That's your pKa's. For example, if you take that plus sodium hydroxide, you're going to get the anion. It's already drawn up there. Let's do it this way. You're going to get the anion plus water. That's 16. That's what, 5? Which side's favored, 5 or 16? This side's favored. So you see the anion is favored if you treat it with sodium hydroxide. Again, the bigger take-home message is organic molecule you can make it soluble in water by converting it into an ion. The most common way to convert things to an ion, just about the only way, is acid-base chemistry. You got to be able to recognize acids, recognize bases, etc. Any questions about this process? And the same one that was asked earlier from the lab manual, basically it was the same thing. It was asking which one's soluble in sulfuric acid. Yep. Here, basically, which one's going to be soluble in sodium hydroxide. Other questions about acid base while we're on the topic? Question?
Yeah, you said organic substances become soluble in water by becoming an ion. But what about like IMX? Is there ever like a case where the IMX can just call like sugar, right? Sugar doesn't become an ion; it just dissolves.
Right. Sometimes a highly polar organic compound will dissolve in water without becoming an ion. If you just got lots of hydrogen bonding positions, and sugar is a great example. Still, it still takes a little heat. But there are some organic compounds that will just dissolve in water at room temperature without becoming ions. But in general, the best way is to make them ions. That's why the majority of your drugs are ions. Because they got to dissolve in your stomach, which is water, not acetone. Okay. Well, let's move on to confirmations if there are no acid-base questions. And also mention IR. How are we doing on IR? Is there anything here? Test is when? Tuesday? A week from today? Any questions about IR? Questions?
In the book, when we were doing the IR problems, some of them were more, especially for NHPs, some of them were more obvious than others. So how do you, clearly distinguish whether it's an overtone or even if it's small?
Well, it can be difficult to tell if it's an overtone or if it's truly like an NH or OH. Remember, the problems in the workbook, you're assigning compounds to spectrum.
Right.
So it's got to be one of them up there. I think that will help you if you just remember that. Now, if you had nothing to go with, you'd have to say, I don't know if it's overtone or NH, and you'd have to have more information. Other questions about IR? Question?
You mentioned in the video, and I think maybe as well as one of the handouts, sometimes it's either the OH or the NH. They're sometimes not as strong with modern instruments or just like instruments in the lab. On the test, are they going to be obvious, or are they going to be more, not as broad as
It'll certainly be a clear key. It may not be as strong as some of the traditional textbooks, but it won't be so weak that you're going to try to ignore it. Okay, there's probably other things to ask at this point, but we need to get on to confirmations. We have the blue outline, and then we have the the white packet for handout. Pretty much this was a lot of intro stuff, dihedral angle, different ways to look at the compound. And then we started rotating, and we got terminology. And so, ethane here, 2 carbons, each thing on the end is H, carbon 3 H's, okay? This can rotate, this bond can rotate, I can rotate it by actually turning the bond, or I can rotate that all by turning the carbon. That's easier for me to do here, okay? But really the bond is rotating. We got to be able to draw these on the board. We're going to do what's called a Newman conformation, then we're going to have terminology like eclipse, staggered, etc., different energies. But let's do that. Essentially, we're going to get to what's on the other page, this energy diagram. Let's sort of get there. Okay, we can draw this like that on the board. That's on the previous page. How do you draw it like this? Circle, circle, dot, dot. We draw a circle with a dot in the middle. Okay? Now the dot in the middle is supposed to be the front carbon. Okay? Front carbon. What do you see on the front carbon? I see an H coming straight up. And I'll say straight up, it's actually also sort of leaning towards you. Okay? And I'm just going to call it straight up. So on the front carbon, there's an H straight up. All right? We're not going to try to draw it as if it's leaning out towards you. Now also on the front carbon, there's an H going that way to my right. Okay? A little bit down. Okay? So this is like this. Also on the front carbon, we got an H coming this way. So we got something like that. That's the front carbon. Now on the back carbon, I'm actually going to turn this to make it like that. Let's start with that. Which, by the way, is what type of conformation? And general. Two general types. This here, where you can't see this behind it, what do you want to call that? Eclipse. Eclipse. Now when I turn it like that, now there's nothing right behind it. What do you call that one? Staggered. Okay, there's two general types, either eclipse or staggered. Okay? Anti is actually a type of staggered. Okay? But I'm going to do staggered like this, the back. Now the back is behind that carbon. Okay, it's right back there behind it. You can't really see that carbon. Pretend like there's a big quarter or something obstructing this. Okay, I got a big softball sitting right here. Well, it's right here. You can't see that carbon back there, but you can see that H sort of coming down back there. What we're going to do is we're going to draw the back bonds from here. Okay. This is sort of obscuring that in the back, and the back bonds come off of the circle here. So in the back you got one straight down, you got one here, and you got one actually here. There it is on the board. Front carbon is the dot. The bonds coming off the back carbon actually come off that circle. Y'all see this? Anybody is not following me? Just so that's that. What can we see here? This is staggered. All right. We can see dihedral angles. What's the dihedral angle here?
60.
That's a 60-degree Dihedral angle is usually like 5. 60 degrees there. That's basically the angle between, it's a two-plane angle. This plane and that plane. Where this should be straight up, but that's straight up. If we just draw a one-plane angle, we get something like that. This line comes from the front bond, but that line comes from the back bond. Okay? It's two different planes. You got this plane and that plane. All right? So know what a dihedral angle is. Sometimes called a torsional angle. Okay, let's draw this, but let's draw the let's rotate that back and let's draw it eclipsed. To do this, I'm going to draw a circle, circle, dot, dot. The front is actually the same. Okay, the same as over there. I didn't rotate the front. So I got this, this, this. That's the front, just like this. Now in the back, we have an H coming straight up. Here's the back carbon. That H is coming straight up. So we've got to draw it in the back straight up. Well, it's really behind that H. If we draw it straight up, pretend like I just drew it. It's right behind that H. But usually you want to show it there. Otherwise, you don't know if the person actually drew it. So we draw it just a little bit to the side. Okay? And we kind of draw this like this. All right? Now, it's not actually eclipsed because, again, if it was actually fully eclipsed, there would be nothing behind it. You wouldn't be able to draw anything. That's how eclipsed is usually drawn. And that's supposed to be fully eclipsed, and the dihedral angle is what?
0.
Actually 0. I mean, if you measure that, it looks like 2 degrees or something, but, okay. So that's that. Well, we also have H coming here, eclipsed with that H. Okay. Since I drew the back one a little bit to the right, I'm going to draw this one a little bit to the right, or like a clock hand going around. So it's like this, and this one a little bit to the far side of this. So that's sort of everything eclipsed in a Newman projection. Now, which of these is better? This thing can rotate. Is it going to prefer to be eclipsed, or is it going to prefer to be sort of rotated like that? Staggered is always better. Okay. Because this now has more room. It's further away from these electrons. That's 2 electrons there in that bond. These 2 electrons are further away from these 2 electrons. Staggered is always better. Okay? Eclipse leads to the electrons sort of repelling each other. That's sometimes called torsional strain. Now let's do this. Let's hold the front just like we drew it in both of these, with the H straight up. And there we go. I'm going to rotate the back, and we're going to rotate 360 degrees all the way around. Okay, here, all the way around. And let's look at the various energies. Now, I could rotate this 1 degree, but that's not worth considering. Okay, each time I'm going to rotate 60 degrees. Let's consider that. All right, I'm going to rotate the back 60 degrees. That's actually 60 degrees there. So we went from eclipsed, now we're at what? Staggered. And that's actually what we drew here. Because that is that. At 60 degrees. Now which is better, where we started or where we're at now, in terms of energy? This is better in energy. So now this is a lower energy conformation, we call it. And if we plotted that, we would plot this lower than the other. We're not going to be looking at absolute values. Just relative, this is lower than that. We'll see the next page when I'm done here. Now let's rotate another 60. Okay, there we go, another 60. Now what are we back to? Now we're back to the eclipse. Is that eclipse any different from this eclipse?
No.
It's actually no, it's the same, because these are all H's. Now we're back to that high energy, and we rotated a total of 120. Let's rotate another 60 here. Now we rotated 100, total of 180. We went from straight up to straight down. We're back to what now? Staggered? We're back to the lower one again. Is that staggered any different from that staggered? No. Actually, no. 60 more, we get back to eclipse. It's the same as the previous two eclipse. 60 more, we get back to staggered. It's the same as the other staggered. Again, now we're at 360 rotation. We're back to fully eclipsed. If we graph all that, we'll see it's shown top of the next page. And this is what we just did. Okay? This is just potential energy. There's no numbers here. All we see is that this is higher than that. We started with eclipse. We rotated 60 degrees. We went to staggered. Rotated to eclipse. Rotated. And you see, you just go back and forth. One question that can be asked here is how many different types of conformations are possible here as you rotate 360 degrees? There's only two. It's either the eclipse form or the staggered. All the eclipses are the same. All the staggereds are the same. In the next example, not all eclipses will be the same. Again, we usually rotate 60 degrees. You could rotate 1 degree and consider it 1 degree. Just 60 at a time. One turn all the way around. I think that pretty much covers this point. Any questions up to now? Question?
What's the difference between the anti-position and the staggered position? Is that just to get to the
Anti is a type of stagger.
Okay.
It's really not relevant here. We're going to use anti in the next example when we start having groups here, multiple groups. And anti will help us distinguish between different types of stagger. Here we don't have different types of stagger, so it's not needed. Okay, so the next one below, let's go from ethane to butane. So now let's do 4 carbons. 1, 2, 3, 4. And I'm going to actually take these off. And now each thing, carbon, 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 carbon. Now the H's are going to be just the 2 little small things there. Okay? And here. All right? Now look at this. Carbon, carbon, carbon. Okay? How's this going to like to exist? Let's draw these. Let me see how we're going to start. That looks like it's fully eclipsed. Okay. Let's draw what we see here. I reckon I'll start fresh and just get rid of the whole thing. Circle, circle. That's not a circle. A little better. All right. Let's start right here. That is a conformation. Front carbon, I have a methyl straight up. I'm going to do ME. I like to put MEs on my ends. Otherwise, it just looks like a line. I'm wondering what's on the end of that line. Okay. H going here, and H going here. That's what these two H's are doing. Tetrahedral carbon, right? Okay, the back carbon. What do you see on the back carbon? There's a methyl going straight up. It's actually eclipsed by the point in the front. I'm going to draw, I can say it's behind there, we just can't see it, but let's actually put it up there. And let's do something like this. Now look, there's an H over there. It's actually eclipsed with that H. If you look through there, okay, they're kind of small, but they're eclipsed. The back one is eclipsed by the front one. Basically, there's an H on the back. There's an H on the back here. There's that there. Let's rotate, let's see which carbon they're rotating. In the graph, they're actually rotating the front. You'll see that? Okay, so let's hold it right here. I'm going to rotate the front 360 degrees. All right? First, let's turn it 60 degrees. That's going to go there. Basically, to go 60 degrees, the bond that's that way is now going to come straight down. Okay? Now, if we draw that, all right, it's already on the paper. I'm going to draw a couple. I'm not going to draw them all. Let's just do a couple on the board. Circle. What am I rotating? Just the front. So the back is the same, right? I'm not rotating the back, so I'm going to go ahead and draw the back in. Front now, we have methyl coming over here. What's coming straight down?
Hydrogen.
Let's see, the front comes from the dot, and then there's an H here. H here, H straight down. And there that one is. I got so close here. Hopefully you have room on your paper. Okay. That looks eclipsed. This is staggered, right? Things are staggered. Okay. But we're going to have to give this a more specific name. Coach? Here we sort of have groups there other than hydrogens. Here the groups are sort of beside each other. What's German for beside each other? Gauche. I reckon. That's what we call it. We call this gauche. Okay? When your groups are sort of beside each other. Gauche is a type of staggered. Let's rotate this again. Another 60 degrees. What are we going to get? We're not rotating the back, so the back stays like this. Now where's the methyl going to be? It's going to be eclipsed with the H. And so the methyl is going to be now sort of like this. There's an H straight up. I'm going to do that sort of here. And then there's an H coming this way, sort of like this. So we're back to an eclipsed. Let me ask you this. Both of these are eclipsed, but are they the same? No. Which one's worse? It's worse when you have your two big groups sort of clashing with each other. What can we call that? We got two different eclipses. Call this sin. Sin is almost like cis. They're sort of both up towards each other. It's called sin. It's called gauche. It's a type of staggered. This is eclipse, but it's not sin. I don't think there's an official name for that. I call it partial eclipse. Where this sometimes I call total eclipse. But that's just kind of me. I don't think that's an official term. It's eclipsed, but it's not as bad as that. So if you plotted energy, this would be lower energy than this. This is the highest in energy. Let's draw one more. Let's rotate 90 degrees or 180 on the board. What are we rotating here? We're rotating the front or the back? Front. So I'm sort of going to show the front, which has a methyl. I'm going to sort of pull it and rotate it on this way. The back is the same, methyl, H, H. Now the front methyl rotated down here, and we should have H and H. Is this eclipsed or staggered? Staggered. Well, that was also staggered. We call that gauche. What do we call this one? Good. This is called anti. Because your major groups are opposite to each other. Okay? This one's sort of up, this one's down. It's called anti-conformation. What is that called? Syn, anti. What about if it was like that? Gauche to the side. Okay. Which one's the best up here? Anti. Big groups anti is your best. And when we start drawing these with other molecules, and I say draw the best, I'm going to put your big groups anti. Let's look at as this rotates around. Now they're all shown at the bottom here. And they're all labeled with a letter. As I race, be looking at those there. The question that can be asked here is how many different types of conformations are possible as you rotate 360 degrees around? Above, the previous example was only 2. How many here?
Hey, Dr. Stevens.
Yeah.
So when electrons don't have like an adequate amount of room, does that mean that most potential energy is stored in that molecule?
In the what now?
So like, whenever like electrons, if they're not like adequately spaced, that's kind of like why we want anti, because it allows a lot of room for the electrons. Does that mean the most potential energy is stored in there because those electrons don't have a lot of room?
Well, but this can rotate. I mean, the molecule as a whole is probably a summation of all this. But we're looking at individual conformers. Does this compound prefer to exist like that or like this? It prefers to exist anti. Does that mean it can't exist like that? No, it can. This can rotate. We're looking at which is the preferred conformation. We're also looking at just terminology. Preferred is anti. Why? Because electrons do repel each other. And if we ask these electrons to come in here, it's like bringing 2 magnets together. You can feel that potential energy create. Question?
So I have a question about what does this help us understand better, and using this and understanding how this works, does that help us use these?
Right now we're pretty much just kind of
better?
doing it.
Yeah, I don't.
It's a good, what are we going to be doing down the road? When we get to test 3, we'll do eliminations, and we'll say that it has to eliminate an anti-conformation, and the anti-conformation leads to which product? You have to be able to draw the anti-conformation and have to be able to then rationalize which product, because there's more to it. Right now this is introductory, just being able to do it, drawing, and the terminology. Different types of energies possible. For this example, a good question would be how many possible conformations? Energy levels. How many are they? A is like the worst. What was A? A is what? Syn? It's like total eclipse. B and F are the same, correct?
No.
It's the same though.
There are different positions within the same energy.
How many different energy levels are they? B and F is the same. So this is one. You got A, and you go B, which is lower than A. Everybody agree it's lower than A because staggered is always better than eclipsed. Okay, so B should be lower. Then we get to C. What is that? It's eclipsed. So C should be higher than B because eclipse is always worse than staggered. Is C higher? You see how they made it higher? But it wasn't as high as this. Because over here you had your big groups clashing. Here at least your big groups are not clashing. It's not totally eclipsed. Then you go to D. D is the best. That's why D is the lowest energy in the graph. Then actually you start repeating because E is just like, this is just like C, right? So I'm going to do it like that. Maybe that'll help us keep up with it. And F is just like what? E. Yeah, it's got the same energy. And then A is just like what? A is just like A. That makes sense. So how many total different? 1, 2, 3, 4. 5? No.
No, it's just
4. The answer is 4. I think if you look at it, we take a little more time, you can see there's only 4 levels up there. 4 energy levels. Where with ethane, there was just 2. Because now we have 2 different types of staggered and 2 different types of eclipse. That's why there's 4 now. Question?
Is it just a coincidence, or is it the same number of energy levels, the same number of carbons out in the molecule?
I've never looked at that,
Okay.
so it's probably coincidence. Question?
So when you so is there any reason why only the one carbon rotates? Is there any reason why the second?
No, we could have rotated it back.
But is there any reason why only one carbon rotates?
Well, I mean, they can both, but your angle, I mean, one could rotate 30 and the other way 30, but it's still a net 60 rotation. I mean, you just... Question?
Alright, so you have thermoelectric force between 2 groups, right? How would you show that on this diagram? Because I'm pretty sure the lowest energy state would be Sand Eclipse, since we have these this IMF between those 2 groups.
You're arguing that this is lowest energy?
If you have an IMF.
Okay. That's not bad, because we know that, like, methyls may be attracted by van der Waals attraction.
Well, like, if you had not something as weak as a van der Waals, but say something like a hydrogen bomb.
Like on the next example we're going to look at?
Yeah.
Okay. We'll see examples. Yeah, we'll see examples of acceptance. For now, can you draw these? Terminology, relative energy graphing. Okay, let's see what we need to do. On the blue sheet, everything has been said. We're down to the compounds, and let's do this. Show the following compounds in lowest energy conformation. Whenever you're doing this with a cyclic, we're always doing Newman. Circle, circle, dot, dot. Show this in the lowest energy Newman. You guys on the right do the first one. All right. You guys over here do the second one. Lowest energy Newman conformation. Instead, let me do this. Let me do the first one, and then let's do this. You guys still do the second one, but instead, you guys do the third one. Because I'm going to do the first one. Okay, we're going to have to look at these in a particular view. Okay? It says here, looking down the 1,2 bond. Where's the 1 carbon? That's actually from nomenclature. 1 carbon is there, 2 is there. If you named it, that would be the 1 carbon. Okay? Looking down, that means we're going to be looking the 1, 2. Okay? It's like the 1's in the front, 2's in the back. We're looking down the bond. The 1's in the front, 2's in the back. How do we look down with the 2 in the back? We got to stand over here. And we're going to look through there. Okay? On the front carbon. Now first off, we got circle, circle, dot, dot. I'm going to do it over here so I got more room. Front carbon. What do you see on the front carbon? If I'm saying over here, I see something coming straight down. Chlorine is going behind the wall. Okay, what's on this carbon coming forward? Hydrogen. Okay, let me draw the model and then you can see what I'm looking at. Or a big. That's what the model is. We got a chlorine and a fluorine. Let's make fluorine red, chlorine green. Okay? Let's don't worry about what's over there. This carbon here. I got a fluorine coming straight down. That's just missing 1 carbon. That's all that's missing. Here's this over here. The fluorine is here in the plane. It's this way. What's on that carbon going back?
Chlorine.
Chlorine. You see how the chlorine's going back? That's where I made my model like this. What's on that carbon coming towards you guys? See that H coming towards you guys? See a little tiny H there? If I put it there, it's coming. It's like that. You see it coming towards you guys? Okay, there it is. I'm going to draw what I'm looking at. Now, see, I can't turn the board and do this. Instead, you got to come over here and look. If I'm looking at this carbon, what's coming straight down toward my feet?
Chlorine.
The fluorine. Now, it's coming towards me a little bit, but it's coming straight. If I hold it like that, it's coming straight down. Okay? I want to draw what I see. I see a carbon with the fluorine coming straight down. I see a carbon with a fluorine coming straight down. Okay, see, this is me looking at it. All right? I see a chlorine going to the hull or behind the board. So if I'm looking at it and it's going behind the board, is that on my right or left?
Left.
It's on my left. So I'm looking at it, I see a chlorine going that way. Chlorine going that way. Chlorine is here. I see an H coming towards you guys. As I'm looking at it, the H is on my right. I want to draw that right there. That's what I'm drawing. Fluorine straight down, chlorine here, H there. It's just it's on the board like that. Okay? Now what's on the back carbon?
Hydrogen. Coming up.
There are two H's there. I see a ethyl group going up. Going up. One H is coming to my right, and one H is going to the left. So I got ethyl going up, H here, and H here. So this is that compound as drawn on the board, but is that the lowest energy conformation? What do we want here? What's the biggest group on the front carbon? Chlorine. Larger the halogen, larger the group. Now that could differ in some tables, but for us, as you go down the periodic table, it's bigger, more demanding. What's the biggest group on the back carbon? H, H, or ethyl? Ethyl. Right here, as drawn, those two groups are gouged to each other. That's not the best. How do we want them? Anti. How are we going to get them anti? I'm going to rotate one of the carbons. I'm going to rotate the front. Okay? I want to rotate the front. I want the chlorine down here. This means I just rotated. I'm rotating the front. That means the back is not going to change. Now the chlorine's straight down. If the chlorine comes straight down, where does the fluorine go? We're just turning this. Fluorine here. Fluorine's going to come up here. And H is going to move over here. And this is your best. Because your two biggest groups are anti. That's the lowest energy conformation of that molecule. That is, pretend there's another carbon there. That's how it's drawn on the board, but that's not the best. But the best is going to be where this chlorine swings opposite the methyl. This is how this is, right? Chlorine straight down, fluorine there, H here. In the back, ethyl, there's a carbon missing. Two H's. Okay. Now y'all try the next ones. You guys are doing the second one. You guys on my right are doing the third.
Yeah. You want just the final one, or do you want the first and the final?
According to directions, I only want the final. But I would recommend you draw the original so you can then rotate it. Question? Chlorine is bigger.
Doesn't matter how much.
It's basically governed by electron repulsion. The electrons around chlorine are further out because it's a bigger atom. Again, some of this is sort of just what we're doing in class. You can look at the exact tables and you can see there's some slight variations in what I'm telling you. But for us, bigger the halogen, more needing space. See, if I'm looking through here, that fluorine is coming straight down the plane of the board. The H is like that. So if I'm looking at it, the H is to my right. Chlorine is going back behind the hull, so that's to my left. Yeah, but that's the angle of the thing around that curve. That hydro angle is two separate parts. I mean, it's like this. Right here, what's the dihedral angle between my arms? 90 degrees. I mean, this could be 195.
I'm thinking this is a little unless you go the opposite way.
Looking down the 2-3 bond. What's 2 here? Must be that there, yeah? 1, 2, 3. So we want to look down there. Two with 3 behind it. 2's in front, 3's behind it. What do I see on 2? That bromine's coming off the board, right?
Yeah.
If I'm looking down, that bromine's coming off the board like that. It's to my right. It's also sort of going up. The bromine's like this. What's coming straight down to my feet in the plane?
Methyl.
Methyl. What's going back on that carbon that's not shown?
Hydrogen.
Okay, if I'm looking down the board, that H is going back to the hull, so that H is on my left. I'm drawing what I see. Basically, the board has been turned. The board's now like this. The bromine's coming off, and you're sitting over there. The bromine's coming towards you guys. The H is going away from you guys behind the board. There we go. That's the front. Okay, on the back carbon. What's in the plane? That is on the plane of the board. Is the methyl in the plane of the board? No, it's going behind. The plane of the board is this ethyl group. And it's going straight down. It's actually eclipsed with this. It's supposed to be eclipsed. There's a methyl going behind the board, because that's what that dash means. If it's going behind the board, I'm looking at it, that's to my left. Hydrogen's coming forward.
Well, it'd be opposite.
I didn't hear, you said something about a hydrogen.
Yeah, that's, wouldn't it be the hydrogen?
Oh, this one. I thought you were talking about the one that's there. Yes. It's going to be left. Yeah, it's eclipsed with this. Basically, this thing is drawn in an eclipse conformation up there. And then there's an H coming, drawing that H if you want. So if I'm looking back at carbon 3, there's an H going towards you, so that's to my right. So back there in the back, there's an H going to the right, so it's sort of a, okay. That's eclipse. But that ain't the best, is it? Let's rotate the front. How about that? What's the biggest on the back? Methyl or ethyl? Ethyl. What's the biggest on the front? Bromine or methyl? That could be a little bit. Bromine's huge. Okay, bromine. Even though that carbon's got 3 H's on it, I'll try to make these pretty straightforward, and usually I'll have you comparing like methyls to ethyls, okay, and your halogens. But bromine is a lot bigger than a methyl, and so we want the bromine on the front to be anti to the ethyl on the back. All we got to do is just rotate the bromine up here, and we get something that looks like the front. We're not going to change. No, we're not going to change the back. Back is the same, is that right? We just want the bromine to come up here. We're just turning this. So the H is going to come here.
No.
No, it's front carbon, right? We're turning the front carbon. I got to make that the front carbon. And then what's here? Front carbon has a bromine, H, and methyl. Bromine, H, and methyl. 2 big groups are anti. Yes. Now some of these you might want to make an argument about because you could. I'm telling you the best is big groups anti. Now, we do have the methyl and the ethyl kind of gas to each other, close by. And the bromine is close to the methyl. But is this better than this one?
Yeah.
Certainly, because it's staggered. There's occasionally we'll run across one where your 2 biggest groups are anti, and it may not be the best because if we got multiple substituents on there. But for us, it's going to be the best. Okay? Because we want, what I'm asking you to do is always have your biggest groups anti. Done. Okay? Because it could get complicated. You got a lot of constituents. You can say, well, is it better to have this next to that or that next to this? Biggest anti. How we do on this third one? How we do, guys? Let me ask you a question. In your best confirmation, which groups are anti?
Yeah, I remember.
We'll do that one. We'll do that one over here. Before we erase this, let's see if I can ask you a question. What's that dihedral angle between the methyl and ethyl? 60 degrees, right? 60-degree dihedral angle between the methyl and the ethyl. Okay. What's the dihedral angle between the bromine and the ethyl? 180. They're anti. They're opposite. Okay. So you need to know dihedral angles. Let's draw the third one. Looking down the 4-3 bond. If we name this, would that be 1, 2, 3, 4, 5?
No, the other way, because the iodine are.
No, I think this would be the one.
That's what I think.
You'd have 2, 2, 2, 2.
Yeah.
If you came this way, you would only have one group at the 2. Would you rather have one substituent at the 2 or 2 substituents at the 2? 2. I think that. Anybody? I think that's one. Looking down the 4-3, so that means we're over here. It's 4 in the front. That's what I mean by this. 4-3. 4 in the front. Okay? It's supposed to be a circle. What's on 4 carbon? I see something going straight up in the board. What's that?
Iodine.
Methyl. That's a methyl right there. I see something on, that's carbon 4. What's on carbon 4 coming towards you guys? Iodine. So if I'm standing over here like the little man is, and there's an ethyl coming off the board towards you guys, it's on my, okay, I'll draw what I see. What's on the carbon going behind the board? Which if I'm here and it's going behind the board, that's on my, that's an H going behind the board, right? So there's carbon 4. Carbon 3 is behind it. What do you see on carbon 3? Now let's look past there. Now we're looking past carbon 3. What's on carbon 3 going straight down? Straight down on the board. T-butyl group. Tert-butyl? There's supposed to be a circle there. T-butyl group's coming straight down. What's on carbon 3 coming towards you guys? Nothing. It's coming up and towards you guys like that. So if I'm looking, it's on my left. So the methyl is up here. What's on carbon 3 going behind the board? Undrawn H. If it's behind the board and I'm over here, behind the board's on my right. There it is as drawn on the board. Is that the best? What's the biggest group on the front carbon? What's the biggest group on the back carbon? T-butyl. Make these anti. You want to rotate the front or the back? It doesn't matter. I'll rotate the front. I'm going to rotate the iodine up here. So I'm rotating. The iodine is going to move up here. That methyl is going to go here. H is going to come here. I mean, you always have, you know, in real life that's 109.5, but on the board that looks more like 120. So we just rotated the front. The back is going to stay the same. So we've got H, methyl, and T-butyl. So now your iodine and your T-butyl are anti. And that's the lowest energy conformation of that molecule. In the lowest energy conformation, what's the dihedral angle between the iodine and methyl? 60 degrees. How we do, guys? Y'all, that was y'all's over there. Questions about that one? Question?
Yeah, when you ask, like on an exam, if you ask between the methyl and the iodine, would you specify which methyl or?
Why would I need to do that?
Oh, because they're on different phase. My bad.
Questions? Questions, guys? I'll leave it up there. Let's look at the next page.
I have a question. I have mine set up where I have I8. My front one is H is to the right, and then the methyl is on the other side, and then inversely the back one. Does that matter?
No, as long as it's the same compound. But it's not the same compound. I just turned it over. Now you've got your iodine. Your iodine is here, but you have drawn straight up. You have drawn straight up an H. I have a methyl drawn straight up, so I can tell somehow you didn't get it right. Down the bottom of the sheet, guys, a couple of questions, then we'll move to the back side. Can a syn or Gauss conformation sometimes be preferred over an anti? Well, the answer is yes. It's antifreeze here. It's actually known to prefer a Gauss conformation. That is, the two OHs do not prefer to be anti. They prefer to be side or to the side of each other. Why? Hydrogen bonding. These electrons will hydrogen bond to the H. That's an intramolecular hydrogen bond. It makes the Gauss conformation preferred. So the question was that right there. Sometimes there are things that will make other conformations preferred. Basically, this is hydrogen bonding making molecules have certain configurations, conformations. I mean, hydrogen bonding makes DNA have a certain configuration, right? It's called a double helix. Now, this is a hydrogen bond shown within a Newman conformation. Do you always have to show it in a Newman conformation? No. One below, I just wanted to show you. Can you illustrate an intramolecular H bond down here without using a Newman?
Yeah.
Basically, we could draw this molecule What if I redrew it like that? Isn't that the same molecule? Why might I want to redraw it like this? With the OH, instead of like this, you see that can rotate. If this bond rotated, instead of my thumb being that way, the group will now be over here. Why would it prefer to be like that? Hydrogen bonding. So basically, this is a different conformation. But I didn't get into all doing it by the Newman. Okay? But whenever we start doing this type of thing, we're really rotating bonds. Okay? Rotate this arm, and now the hydroxy is like this. So that's another example of an intramolecular hydrogen bond. A way to illustrate it. If you look on the flip side, you can see questions like this. Name the following compounds. Obviously, you have to interpret the Newman conformation and get it back into some way to see the whole thing and name it.
For the previous molecule, what would you do about the nitrogen? Like, how would you demonstrate the ability for the second nitrogen to
I don't think this can hydrogen bond to both nitrogens. I mean, the other nitrogen's way over here. It's only going to hydrogen bond internally one way. Think about it, draw it out, and show it to me. But I don't see it right here. Okay, let's try the first one here. Can you? I'll probably do this one and let you do that one on your own. When you see something like this, I recommend just drawing it out in a more standard way. I got a carbon in the front. What's on the carbon in the front? A methyl. Now you got to be, there's two parts to this. I only asked you to name it. And so we don't really need to keep track of the stereochemistry. But we should go ahead and do that. Because if we don't do it now, we're going to wonder why a little bit later. Okay. Carbon in the front. I see a methyl going straight up. Pretend I'm over here. You're going to draw this bromine dashed or bold. looking at that carbon, it's going to your right, correct? So if I'm looking at that carbon, it's going to my right, do I want it dashed or bold? Bold. And thus the other 1, 2, 3, the butyl group is going to be dashed. 1, 2, 3, 4. Okay? There's that. Now that's bonded to a carbon. That's the carbon in the back. What's coming off that carbon?
2 hydrogens and a fluorine.
Yes. Now, you actually don't have to worry about stereochemistry there because it's not chiral. Don't worry about that now. What I did in the front, we're going to need to worry about that come test too. That's why I did it now. Okay. Basically, there's your molecule. And I showed the 2 carbons out instead of having them front and back like that. Longest continuous chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I see 2 6s. Which one is the best? 4, 5, 6. If it's that one, how many substituents on it? 3. If it's 1, 2, 3, 4, 5, 6, how many substituents?
3.
2. Only 2. That would be a complex. The one I circled is the best, and that's what, hexane? What's on the hexane? I see a methyl, a bromo, and a fluoro. What's the 1 position? 1, 2, 3, 4, 5, 6. By doing it this way, we have subs at 1, and then subs at both of 2. Alphabetical, what, bromine? 2 bromo, 1 fluoro, 2 methyl, hexane. Does that look right? I just chose to maintain this perspective here, just to sort of reinforce that. That will be needed a little bit later. It wasn't needed in this question here, though. Do that one on your own for Thursday. We need to move down below. Time is flying. So that's your alkane conformations, okay? These rotations. Let's now look at cycloalkanes. In particular, we're only going to look at cyclohexane, okay? I have a cyclohexane here. Here I have a benzene ring, okay? What do you see the big difference? The benzene ring with the 3 double bonds. Okay, because of the double bonds, every atom is sp2, every atom is planar, and you have a planar ring. Okay? Planar. Every carbon's sp2 planar, and they're all planar together. It's a benzene ring. Cyclohexane ring, on the other hand, just being like this with no pi bonds, every carbon is sp3. Because of that, it's not planar, and instead it exists in what we say as a chair or boat conformation. This thing has some flexibility. This thing can pull down, this can go up. I don't know how well you guys can see that. We'll start drawing it on the board and just see it as a drawing. That right there is called a chair conformation, where if you're kind of sitting here and this is sort of the back of the chair, and this is sort of hanging over where your legs would kind of lay over, like you're sitting there, okay? Now this end could pop up, and that's actually called a boat conformation. That's analogous to like an Italian gondola with the boat and the two ends sort of coming up. Okay? Your boat is never good though, because the boat, these two H's up here sort of clash. That's called flagpole interactions. Okay? Your chair is always best. And from now on, I will only talk about chair. So we're going to pull that back down. The important thing for the remainder of time is how do you draw this on the board? Okay? Because this is not sufficient. That looks flat and planar. How do we show the 3D nature there? Okay. We want to start this with two sort of offset parallel lines. That right there is 4 carbons. 1, 2, 3, 4. We're just going to connect this with 1 carbon. Connect these. That's going to be like this. Over here, we're going to connect these with down. Ever can't see, please go. So there we go. These models are just so small for the size we have here, class size. But you sort of sit here. This is sort of the back. Sometimes you see drawings in textbooks with the little guy here, the feet hanging over, and the back here, but I'm a terrible drawer. From here, we have to put in the hydrogens, though. The carbon has 2 hydrogens. How do we draw those in? We have what I call up and down hydrogens, and then to the side. Or also up and down carbons. This is an up carbon. This is like a point that's up. An up carbon gets a straight up hydrogen. This is sort of a down carbon. It's like the point that's down. It gets a straight down hydrogen. See, all your up carbons, there's 3 up carbons. I call this, and that your up carbons. They get straight up H's. This one you can draw sort of like short, or you can draw it past that. Either way you want to do it. You could bring it all up here. This carbon is actually in front of that one back there. Okay? Sort of like this. Okay? This is 1H, that's the other one in the back. So there's a kind of a stereo view here. Now your down carbons get down H's. So that's a down H, that's a down, and this one's down. So there's half of your H's. All the H's on the board are called axial. Axial H's are either straight up or straight down. You guys don't have different color probably, but I'm going to draw the other H's in black. The other H's are going to be called equatorial. This one's going to be drawn in like this. Now your equatorial bonds are parallel to not the bond there that's connected to that carbon, but the second bond. That bond is parallel with these two. And this is called equatorial, like the equator. They come out to the side. This bond, okay, we're not just going to draw it straight to the side. It's going to be parallel, not to that bond there, but the next one. And so this is actually sort of up a little bit. That and that are parallel. But it's still equatorial because it's not straight up. Every carbon is going to have an equatorial and an axial. marker's a little bit dim here. Let's see if I can get it drawn in. This one here. This one's going to be not parallel to that, but the next bond. So it's that. That and that are parallel. This here is not parallel to that, but the next one. So that and that are parallel. This one here is parallel not to that one, but the next one. So it's like this. The H here is not parallel to that one, but that one. And so it's, these are supposed to be parallel there. There are all of your H's drawn in. The important thing now is, can you draw your axial versus your equatorial? Questions? Wish we had 10 more minutes. Questions?
Do you have to draw those in every time we draw a shear structure?
Not necessarily,
Okay.
but you do know how to draw them in when asked.
Okay.
Let me finish up. Ask me after class. My lab group, please remain and get your lab. Let me also set the stage for Thursday. Your questions here. Please be looking at these questions. So we're going to have to do this pretty quickly. Okay? I'm going to be basing it on some of your questions. Okay? Please do these. Please do reading. Question? What is that parallel to?
Not the one on the left?
Is it parallel to that one? Is it parallel to that one? Yes. Not the bond that's connected to that carbon, but the next one. Okay, guys, take off.